Cold fusion. On March 23, 1989, two respected electrochemists held a press conference that shocked the world. Stanley Ponce from the University of Utah and Martin Fleischmann from the University of Southampton announced they had achieved nuclear fusion at room temperature using a simple tabletop apparatus. Cold fusion. If true, it would revolutionize energy production, providing unlimited clean power from seawater. The announcement made international headlines. Governments and universities rushed to replicate the experiment, and then it all fell apart. Ponce and Fleischmann's setup was remarkably simple. They used an electrochemical cell with a palladium cathode and a platinum anode immersed in heavy water, which is water where normal hydrogen is replaced with deuterium. They ran an electric current through the cell. According to their measurements, the cell produced excess heat, far more than could be explained by any chemical reaction. They also claimed to detect neutrons and tritium, byproducts of nuclear fusion. Their interpretation was that deuterium nuclei were somehow fusing inside the palladium lattice at room temperature, releasing energy. The scientific community reacted with a mixture of excitement and skepticism. Nuclear fusion normally requires temperatures of millions of degrees, like in the sun or in hydrogen bombs. The idea that it could occur at room temperature in a jar of water seemed impossible. But Ponce and Fleischmann were credentialed scientists with decades of experience in electrochemistry. The University of Utah held the press conference before peer review, hoping to establish priority for what could be the most important discovery of the century. Within weeks, laboratories around the world attempted to replicate the experiment. Most found nothing. No excess heat, no neutrons, no signs of fusion. Some labs reported positive results initially, but couldn't sustain them. By May 1989, the American Physical Society held a special session on cold fusion, where multiple researchers presented failed replication attempts. The consensus quickly formed that Ponce and Fleischmann had made a mistake. What went wrong? Several problems emerged. The excess heat measurements were difficult and prone to error. The cells had to run for weeks, during which temperature fluctuations, chemical reactions, and electrical resistance changes could all affect measurements. The neutron detection was questioned because the neutron levels were far too low for the amount of heat being produced. If fusion was occurring, there should have been enough radiation to kill everyone in the lab. Some researchers suggested measurement errors. Others proposed that the excess heat came from chemical reactions in the palladium that weren't properly accounted for. Some speculated that Ponce and Fleischmann had fooled themselves, seeing patterns in noisy data because they wanted to believe. The cold fusion controversy destroyed careers. Ponce and Fleischmann faced intense criticism and eventually left the mainstream science. The University of Utah's reputation suffered. The term cold fusion became synonymous with pathological science, experiments where researchers convince themselves they're seeing effects that don't exist. But here's where it gets interesting. A small community of researchers has continued working on what they now call low-energy nuclear reactions, or LENR. They claim to occasionally see excess heat in similar experiments. In 2004, the U.S. Department of Energy reviewed the field again and concluded that while some results were intriguing, there was still no convincing evidence for nuclear reactions. Some experiments continue to show anomalous heat, but it remains sporadic and unreliable. No one has produced a cold fusion reaction that works consistently and can be independently verified. The cold fusion saga represents one of science's most dramatic failed replications. What seemed like a revolutionary breakthrough turned out to be irreproducible. Whether it was experimental error, self-deception, or something we still don't understand, remains debated. Faster-than-light neutrinos. In September 2011, scientists at the Opera experiment in Italy announced an impossible result. They had measured neutrinos traveling faster than the speed of light. If true, this would overturn Einstein's theory of relativity, one of the most tested and verified theories in all of physics. The speed of light is supposed to be the cosmic speed limit. Nothing can travel faster, and yet Opera's measurements showed neutrinos making the 730-kilometer journey from CERN in Switzerland to Gran Sasso in Italy about 60 nanoseconds faster than light would take. The Opera collaboration consisted of over 160 researchers from multiple countries. They weren't amateurs or fringe scientists. They were established physicists using sophisticated equipment. The experiment involved shooting beams of neutrinos, ghostly particles that barely interact with matter, through the Earth from CERN to detectors in Italy. By precisely measuring when neutrinos left CERN and when they arrived at Gran Sasso, they could calculate the particle's speed. The measurements showed neutrinos arriving about 60 nanoseconds earlier than expected, 60 billionths of a second. It's an incredibly tiny amount of time, but the researchers' error margins were much smaller, only about 10 nanoseconds. Statistically, this was a 6 sigma result, meaning the probability of it being a random fluke was less than 1 in a billion. The opera team knew how extraordinary their claim was. They didn't announce a discovery. They presented their data and explicitly asked the scientific community for help finding what might be wrong. As Carl Sagan said, extraordinary claims require extraordinary evidence, and the researchers knew their evidence needed to be bulletproof. The scientific community immediately began looking for problems. The measurement required incredible precision. The neutrino beam duration at CERN had to be synchronized with the detection time at Gran Sasso. This required atomic clocks at both locations, GPS satellites for synchronization, and precise knowledge of the distance between the sites. Any small error in timing or distance would produce incorrect speed calculations. Within months, problems emerged. In February 2012, the team discovered that a fiber optic cable connecting a GPS unit to a computer had not been properly attached. This could have introduced a delay in time measurements. Additionally, an oscillator used to timestamp events was running fast. When these issues were corrected, the faster-than-light effect disappeared. In July 2012, after repairs, new measurements showed neutrinos traveling at exactly the speed of light, within experimental error. The anomaly was gone. Other neutrino experiments, including Icarus at the same laboratory and MINOS in the United States, also measured neutrino speeds consistent with the speed of light. The opera result was a measurement error. A loose cable and a faulty oscillator had created an effect that appeared to break the laws of physics. The episode is often cited as an example of science working correctly. The researchers were skeptical of their own results, publicly asked for scrutiny, and when errors were found, they corrected them and published the new results showing they were wrong. But imagine the alternate timeline where that cable had been properly connected. The results still would have been wrong, but would anyone have found the problem? This highlights how difficult experimental physics can be. With complex equipment, tiny timing errors, and measurements at the limits of precision, even careful scientists can get misleading results. Arsenic-Based Life. In December 2010, NASA held a press conference to announce a discovery that would impact the search for extraterrestrial life. A team led by astrobiologist Felisa Wolf-Simon had found bacteria in Mono Lake, California that could supposedly survive and even grow by incorporating arsenic into their DNA instead of phosphorus. This would expand the definition of life as we know it. All life on Earth uses 6 essential elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. If life could substitute arsenic for phosphorus, it meant life might be possible in environments we'd previously considered uninhabitable. The bacterium, designated GFAJ1, was isolated from Mono Lake, which has naturally high arsenic concentrations. The researchers grew the bacteria in media with high arsenic and no added phosphorus. According to their paper published in the journal Science, the bacteria not only survived but grew, and chemical analysis suggested they had incorporated arsenic into their biomolecules, including DNA. This was revolutionary if true. Arsenic and phosphorus are in the same column of the periodic table, meaning they have similar chemical properties. But arsenic is toxic to life specifically because it's similar enough to phosphorus to interfere with biological processes, but different enough to break them. The idea that life could actually use arsenic seemed to violate biochemistry fundamentals. The scientific community reacted with immediate skepticism. Within days, researchers were pointing out problems with the study. The bacteria had been grown in media with no added phosphorus, but that doesn't mean no phosphorus at all. Phosphorus is everywhere, in trace amounts in chemicals, in the air, in dust. The bacteria might have been scavenging tiny amounts of phosphorus from contamination and barely surviving, rather than thriving on arsenic. The chemical analysis that supposedly showed arsenic in DNA was also questioned. The methods used couldn't definitively distinguish between arsenic incorporated into DNA and arsenic that was just stuck to the surface of molecules or contaminating the samples. Multiple laboratories attempted to replicate the findings. The results were negative. When other researchers grew GFAJ1 in low phosphorus, high arsenic conditions, the bacteria survived but grew extremely slowly and showed signs of stress. When researchers used more sensitive analytical techniques to look for arsenic in the bacteria's DNA, they found no evidence of incorporation. The bacteria needed phosphorus, even if only trace amounts, to grow. In 2012, 2 papers published in Science systematically dismantled the arsenic life claims. Researchers showed that GFAJ1 was not incorporating arsenic into its DNA. The bacteria could tolerate high arsenic levels and survive on very low phosphorus, which was interesting but not revolutionary. It was just a hardy bacterium adapted to an extreme environment, not a new form of life. What went wrong? The most charitable interpretation is that Wolf-Simon's team made mistakes in their chemical analysis and misinterpreted their data. The less charitable view is that they were so excited by the possibility of arsenic-based life that they didn't rigorously rule out alternative explanations. NASA's decision to hold a press conference before the scientific community could properly vet the work also drew criticism. The Arsenic Life episode is a cautionary tale about extraordinary claims and the replication crisis in science. A high-profile paper in a prestigious journal turned out to be wrong because the experiment couldn't be replicated and the evidence wasn't as strong as initially claimed. The Mpemba Effect. Take 2 identical containers of water, one hot and one cold. Put them both in a freezer. Which freezes first? Logic says the cold water should freeze first. It has less heat to lose. But according to the Mpemba Effect, named after a Tanzanian student who observed it in the 1960s, the hot water sometimes freezes first. This seemingly impossible result has been observed repeatedly since ancient times. Aristotle mentioned it. Francis Bacon wrote about it, but modern science can't consistently replicate it or explain why it happens. The effect is named after Erasto Mpemba, a secondary school student in Tanzania. In 1963, while making ice cream in a school cooking class, Mpemba noticed that his hot ice cream mixture froze faster than his classmates' cooled mixtures. When he mentioned this to his teacher, he was told it was impossible. Later, a physics professor visited the school, and Mpemba asked him about it. The professor, Dennis Osborne, tested it himself and confirmed that hot water could indeed freeze faster than cold water under certain conditions. They published a paper together in 1969. The paper sparked interest because the effect seemed to violate thermodynamics. How can water that starts at a higher temperature freeze before water starting at a lower temperature? It has to cool through all the same temperatures the cold water goes through, plus all the additional cooling from its higher starting point. It should always take longer. Researchers have proposed numerous explanations. Evaporation means the hot water loses mass as steam, so there's less water to freeze. Convection currents in hot water might cause more uniform cooling. Dissolved gases that leave hot water might affect freezing. Supercooling might occur less in water that was previously heated. The chemical composition might change when water is heated, affecting hydrogen bonding. But here's the problem. The Mpemba effect is maddeningly inconsistent. Some experiments show hot water freezing faster. Others show no effect or cold water freezing faster as expected. The results seem to depend on subtle factors like container shape, water purity, freezer temperature, air currents, how you define freezing, and variables researchers haven't even identified. In 2012, the Royal Society of Chemistry held a competition asking for the best explanation of the Mpemba effect. They received hundreds of entries, but no definitive answer. In 2016, researchers claimed to have explained it through molecular-level changes in hydrogen bonds, but this hasn't been universally accepted. In 2020, a team of researchers argued that the Mpemba effect might not be a single phenomenon, but several different effects that appear in different conditions. Sometimes evaporation is the main factor. Sometimes it's convection. Sometimes it's dissolved gases. There's no single Mpemba effect to explain. Some physicists now question whether the Mpemba effect is even real in a meaningful sense. If the phenomenon only occurs under specific hard-to-control conditions, and most attempts to observe it fail, is it a genuine physical effect or just an artifact of particular experimental setups? The Mpemba effect remains one of the most frustrating phenomena in physics. It's simple enough that anyone with a freezer can try it, yet complex enough that professional physicists can't consistently reproduce or explain it. It's a reminder that even simple systems can harbor deep mysteries. The EM drive. In 2001, British aerospace engineer Roger Scheuer announced he had invented a revolutionary propulsion system. The EM drive, short for electromagnetic drive, was a conical chamber that supposedly produced thrust when filled with microwaves. No propellant needed, no exhaust. Just electricity creating microwaves inside a specially shaped cavity, somehow producing thrust. If it worked, it would revolutionize space travel. But it violates the conservation of momentum, one of physics' most fundamental laws. And despite repeated experiments showing thrust, no one can make it work reliably or explain how it could possibly function. The EM drive is a truncated cone made of copper or similar metal. Microwaves are generated inside the cavity. According to Scheuer, the shape of the cavity causes microwave radiation pressure to be asymmetric, producing net thrust toward the wide end of the cone. This would be a reactionless drive, producing thrust without expelling mass. The problem is, this violates Newton's third law. For every action, there's an equal and opposite reaction. Rockets work by expelling mass in one direction, producing thrust in the other. A reactionless drive that produces thrust from internal processes alone shouldn't work according to known physics. Yet multiple research groups have measured thrust from EM drive prototypes. In 2006, Chinese researchers reported positive results. In 2014 and 2015, NASA's EagleWorks laboratory at Johnson Space Center tested an EM drive and measured tiny amounts of thrust in a vacuum. The thrust was extremely small, about 1.2 millinewtons per kilowatt, but it was consistently in the expected direction. These positive results sparked huge interest. If the EM drive worked, even with tiny thrust, it could enable long-duration space missions without carrying tons of propellant. Scientists proposed missions to Mars, missions to other star systems, all powered by this impossible engine. But replication attempts told a different story. When researchers built EM drives following the same designs, results were inconsistent. Some measured thrust, others measured nothing. Some measured thrust in unexpected directions. The thrust measurements were always at the very edge of what the equipment could detect, raising questions about whether it was real or just noise. Multiple sources of error were identified. Thermal expansion of the test setup could create apparent thrust. Air currents, even in partial vacuum, could push on the device. Interactions between the device's cables and Earth's magnetic field could produce forces. The microwave energy could be leaking out and pushing against the test chamber. In 2018, a team of German physicists built a highly sensitive test rig, specifically designed to eliminate these error sources. They tested both an EM drive and a dummy load that looked identical but had no cavity resonance. Both produced the same tiny thrust signals, proving the effect was an artifact of the test setup, not real thrust from the EM drive. By 2020, the scientific consensus was that the EM drive doesn't work. The thrust signals were measurement errors. The NASA results, while intriguing, were below the threshold of experimental noise and couldn't be verified. No theoretical framework that explains how it could work has survived scrutiny. But a small community of enthusiasts continues to believe the EM drive might work, arguing that all the negative results just mean the conditions weren't right. The debate continues online, but mainstream aerospace engineering has moved on. The EM drive saga shows how difficult it is to measure tiny forces accurately. It also shows how much we want revolutionary technologies to be real, sometimes more than the evidence supports. Polywater. In the 1960s, Soviet scientist Nikolai Fedyakin discovered what appeared to be a new form of water. When water was condensed in tiny quartz capillaries, it had different properties than normal water. It was more viscous, had a higher boiling point, lower freezing point, and different density. The discovery was confirmed by Boris Derjagin, a prominent Soviet scientist who published papers in prestigious journals. Western scientists took notice. By the late 1960s, labs around the world were trying to make and study this anomalous water. It became known as polywater, theorized to be water molecules that had polymerized into a new structure. The polywater phenomenon sparked intense research. If water could exist in a new, more stable form, the implications were enormous. Some scientists warned that if polywater was truly more stable than regular water, it could theoretically convert all Earth's water into this new form, ending all life. This doomsday scenario was mostly speculation, but it added drama to the controversy. Western laboratories attempted to replicate the Soviet results. Some succeeded in creating water with anomalous properties and capillaries. The substance was real, or at least something was happening. Scientists proposed complex theories about water molecule bonding and polymeric structures, but skepticism grew. The amount of polywater that could be produced was always tiny, barely enough for analysis. The anomalous properties varied between experiments. Some researchers couldn't produce it at all, and the theoretical chemistry required for water molecules to polymerize didn't make much sense. In 1973, the mystery was solved. Detailed chemical analysis revealed that polywater wasn't a new form of water at all. It was regular water contaminated with silica and other compounds leached from the quartz capillaries. The viscosity, the change freezing and boiling points, all the strange properties were explained by dissolved impurities. The tiny capillaries provided huge surface area for contamination relative to the small amount of water, leading to highly contaminated samples. Once this was understood, polywater research collapsed virtually overnight. Papers that had been published in top journals were quietly forgotten. The scientists who had promoted polywater didn't face serious consequences because the field moved on quickly once the error was identified. It was treated as an honest mistake. The polywater episode is a classic example of pathological science, a term coined by chemist Irving Langmuir. It refers to research that follows the forms of science but is actually self-deception. Warning signs include effects at the limit of detectability, claims of great accuracy despite weak signals, theories contradicted by established knowledge, and critics who can't replicate results being dismissed as incompetent. Polywater shows how entire research communities can convince themselves of something that isn't real. The Soviet scientists weren't frauds. They really did see anomalous water, but they misinterpreted contamination as a new phenomenon. When Western scientists replicated the contamination, they thought they were replicating polywater. Only careful chemical analysis revealed the truth. Memory transfer via RNA. In the 1960s, psychologist James McConnell conducted experiments that seemed to show memory could be transferred from one organism to another by feeding it RNA from a trained donor. The experiments used planaria, tiny flatworms that can regenerate from cut pieces. McConnell trained planaria to respond to light by pairing it with electric shocks. Then he cut the trained worms into pieces. When the pieces regenerated into new worms, both the head pieces and the tail pieces retained the learned behavior. Even more surprisingly, when untrained planaria were fed minced remains of trained worms, they too acquired the trained response. These results suggested that memories were chemically encoded in RNA molecules and could be transferred between organisms. If true, this would revolutionize neuroscience and potentially lead to technologies for transferring knowledge and memories between people. McConnell published his results in major journals and even started his own journal, the Worm Runner's Digest, which mixed serious research with humor. The scientific community was divided. Some researchers replicated McConnell's results. Others found no memory transfer at all. The planaria system was tricky to work with. The worms are tiny, their behavior is difficult to quantify, and distinguishing learned responses from instinctive reactions was challenging. Through the 1960s and early 1970s, hundreds of papers were published on planaria memory transfer. The debate was fierce. McConnell became a controversial figure, seen by some as a pioneer and by others as promoting questionable science. He received death threats from anti-vivisectionists and was targeted by the Unabomber, who injured him with a mail bomb in 1985. Eventually, the memory transfer hypothesis collapsed. As neuroscience advanced, researchers learned that memories are encoded in the patterns of neural connections, not in RNA molecules. RNA plays roles in protein synthesis and gene regulation, but it's not a memory storage medium in any direct sense. The apparent memory transfer in planaria was likely an artifact of how the experiments were conducted. The worms might not have been learning at all, just showing sensitization responses. Or the transfer was an illusion created by experimenter bias and selective reporting. By the 1980s, planaria memory transfer was considered discredited. Modern research has found interesting results about epigenetic memory and prion-like protein mechanisms that can transfer some biological information, but nothing like McConnell's claimed RNA memory transfer. The planaria experiments remain a cautionary tale about replication. Multiple labs claimed to replicate McConnell's results, but they couldn't all be right because results contradicted each other. Some found memory transfer from head to tail pieces, but not from feeding. Others found transfer only through feeding. The heterogeneity of results should have been a warning sign. Room temperature superconductors. Superconductivity, the phenomenon where materials conduct electricity with zero resistance, normally requires extremely cold temperatures, close to absolute zero. For over a century, physicists have dreamed of finding or creating superconductors that work at room temperature. Such a material would revolutionize power transmission, transportation, computing, and countless other technologies. Over the years, multiple research groups have claimed to achieve high temperature or even room temperature superconductivity. These announcements generate enormous excitement, and then they fall apart when nobody can replicate them. The most dramatic recent case involved Ranga Dias of the University of Rochester. In 2020, Dias and colleagues published a paper in Nature claiming they had created a room temperature superconductor. The material was a hydrogen-sulfur-carbon compound subjected to extreme pressure, about 2.6 million times atmospheric pressure. At this pressure and at 15 degrees Celsius, about 59 degrees Fahrenheit, the material showed zero electrical resistance. It was the holy grail. The paper generated massive media attention. Room temperature superconductivity was portrayed as imminent, but problems emerged quickly. Other researchers couldn't replicate the results. The data in the paper showed unusual smoothness that suggested processing or manipulation. Questions arose about the analysis methods. In 2022, Nature conducted an investigation and retracted the paper, citing concerns about data processing and the inability of other researchers to verify the results. Dias disputed the retraction, claiming his results were valid and that replication failures were due to others not using exactly the right conditions. But this wasn't Dias's first controversy. In 2021, a different paper of his on another superconductor had been retracted from physical review letters after questions about data reliability. In 2023, Dias published another paper claiming room temperature superconductivity in a different material, this time at lower pressure. Again, skepticism was immediate. The patterns were repeating. In 2024, the University of Rochester launched an investigation into research misconduct allegations against Dias. As of this writing, the situation remains unresolved, but the scientific community has largely dismissed his superconductivity claims as unreplicable. This isn't the first room temperature superconductor controversy. In the 1980s, claims about high-temperature superconductivity in certain materials sparked both legitimate breakthroughs and false leads. In 2018, a team claimed superconductivity at near-room temperature in lanthanum hydride at high pressure, results that were partially replicated but remain contentious. The pattern is familiar. A team announces extraordinary results. Initial excitement is followed by replication attempts that fail or produce contradictory data. Questions arise about the original experiment's methodology or data analysis. Eventually, the scientific consensus becomes that the original results were either errors or artifacts. Room temperature superconductivity may eventually be achieved. The theoretical framework suggests it's possible, but multiple high-profile claims have failed to produce a material that reliably and reproducibly shows superconductivity at practical temperatures and pressures. The Hutchison Effect. In 1979, Canadian inventor John Hutchison claimed to have discovered a phenomenon that produced effects including levitation of heavy objects, metal transmutation, spontaneous heating and melting of materials, and disruption of electronic equipment. He attributed these effects to interactions between multiple electromagnetic field generators operating simultaneously. Videos appeared to show objects floating, metal bars bending without applied force, and other impossible phenomena. The Hutchison Effect, as it became known, attracted attention from researchers interested in breakthrough propulsion and materials science. But no one outside Hutchison's lab has been able to produce these effects, and skeptics argue the videos show magic tricks and experimental artifacts rather than real physics. Hutchison's experimental setup was a cluttered assemblage of Tesla coils, Van de Graaff generators, radio frequency equipment, and other electromagnetic devices, all operating simultaneously in a small space. He claimed this created complex electromagnetic interactions that produced the anomalous effects. The demonstrations were documented on video, showing what appeared to be heavy objects levitating, metal samples bending or breaking spontaneously, and wood and metal fusing together. In the 1980s, some legitimate researchers took the Hutchison effect seriously enough to investigate. Representatives from aerospace companies and government laboratories visited Hutchison's lab. Some claimed to witness anomalous effects, though always under conditions controlled by Hutchison. The U.S. military reportedly funded some research related to the phenomena. However, attempts to replicate the Hutchison effect in controlled laboratory settings consistently failed. Researchers set up similar equipment configurations and saw nothing unusual. When skeptics analyzed Hutchison's videos carefully, they identified signs of trickery. The levitating objects appeared to be on wires or filmed in unusual orientations to create illusions. The bending metal could be explained by thermal effects or pre-stressing. The apparent fusion of materials looked like epoxy or welding. Hutchison's demonstrations became increasingly controversial. He refused to allow independent researchers to fully control experimental conditions. His equipment kept breaking down at crucial moments. He claimed the effects were difficult to produce and highly sensitive to conditions, making replication nearly impossible. These are all hallmarks of pathological science or fraud. By the 1990s, the mainstream scientific community had dismissed the Hutchison effect as a combination of misinterpreted electromagnetic phenomena, experimental artifacts, and deliberate deception. However, a fringe community of believers continued to promote the Hutchison effect as evidence of suppressed revolutionary technology. The Hutchison effect represents the extreme end of unreplicable experiments, unlike cold fusion or polywater, where credentialed scientists working at legitimate institutions made honest errors. The Hutchison effect involves an amateur inventor making extraordinary claims without rigorous methodology. The lack of replication, the refusal to allow independent verification, and the accumulating evidence of trickery all point to the Hutchison effect, being pseudoscience rather than a genuine unexplained phenomenon. Yet, it's worth including because it shows how even obvious failures of replication can maintain true believers. If you search online, you'll still find people citing the Hutchison effect as real, claiming that scientists are closed-minded or that the technology has been suppressed. The inability to replicate doesn't end the belief for everyone. The Pioneer Anomaly. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, were humanity's first probes to the outer solar system. After completing their primary missions, they continued outward, becoming the most distant human-made objects at the time. But as they traveled, mission controllers noticed something strange. The spacecraft were slowing down more than expected, not by much, just a tiny fraction of the acceleration they should have experienced from the sun's gravity, but the effect was consistent and couldn't be explained by known forces. This became known as the Pioneer Anomaly, and it suggested either an error in our understanding of gravity or an unknown force acting on the spacecraft. The anomaly was discovered when researchers carefully analyzed the radio signals from Pioneer 10 and 11. By measuring the Doppler shift in the signals, they could determine the spacecraft's velocity with extraordinary precision. The analysis showed that both spacecraft were experiencing an unaccounted-for acceleration toward the Sun of about 8.74 x 10^10 meters per second squared. This is minuscule, less than a billionth of Earth's surface gravity, but it was consistent over years of observations and couldn't be explained by known effects like solar radiation pressure, gravitational influences from planets, or spacecraft malfunctions. The discovery sparked intense interest because any deviation from predicted trajectories could indicate new physics. Some physicists proposed modifications to gravitational theory. Others suggested dark matter interactions or unknown forces. The Pioneer Anomaly became one of the most studied unsolved problems in physics. Multiple research groups analyzed the Pioneer data, looking for conventional explanations. Every known source of acceleration was calculated and accounted for. Solar wind, radiation pressure, gravitational perturbations from planets, outgassing from the spacecraft, thruster firings, everything. None could explain the anomaly fully. But here's the twist. Unlike other entries on this list, the Pioneer Anomaly was eventually explained, though it took decades. The solution came from careful analysis of the spacecraft's thermal properties. The Pioneer spacecraft had radioisotope thermoelectric generators, nuclear power sources that produce electricity from radioactive decay. These generators produce heat, and that heat radiates into space. The key insight was that this thermal radiation wasn't being emitted equally in all directions. The geometry of the spacecraft meant more heat was radiated toward the back than the front. This created a tiny rocket effect, pushing the spacecraft backward, which from Earth's perspective looked like deceleration. In 2012, a comprehensive study that included detailed thermal modeling showed that thermal radiation could account for the entire Pioneer Anomaly within the error margins. The mystery was solved. No new physics was needed. It was just an engineering effect that hadn't been properly calculated initially. So, why include the Pioneer Anomaly on this list? Because for over 30 years, multiple research groups tried and failed to replicate the calculations that would explain the anomaly using conventional physics. It was only when researchers had access to complete spacecraft engineering data and modern computational tools that the full thermal model could be constructed. The anomaly was real, consistently observed, and genuinely mysterious for decades. It just turned out to have a mundane explanation. The Pioneer Anomaly represents a different kind of replication failure, not of an experiment, but of calculations and models. For years, the calculations that should have explained the observations didn't match reality. Finally, more detailed calculations succeeded. It's a reminder that sometimes what can't be replicated is the theoretical understanding rather than the experimental observation. These 10 experiments represent some of science's most fascinating replication failures, from cold fusion's promise of unlimited energy to faster-than-light neutrinos that could overturn relativity, from impossible engines that violate conservation laws to bacteria that supposedly rewrote the definition of life. Each experiment initially seemed to reveal something revolutionary about reality. What went wrong? The causes vary. Sometimes it was measurement error, like the loose cable that created the faster-than-light neutrino illusion. Sometimes it was contamination, like the silica impurities that created Polywater. Sometimes it was misinterpretation of data, like the Arsenic Life study that didn't properly rule out phosphorus contamination. Sometimes it was wishful thinking, like the EM drive experiments that measured noise and called it thrust. And sometimes, like the Hutchison Effect, it appears to have been deliberate deception. But these failures teach important lessons. First, extraordinary claims really do require extraordinary evidence. When an experiment produces results that violate well-established physical laws or biological principles, extreme skepticism is warranted. Second, replication is essential. A result that can't be independently verified by other researchers using the same methods is not scientific knowledge. Third, experimental error is always possible, even in careful studies by credentialed researchers using sophisticated equipment. Fourth, the desire for revolutionary breakthroughs can bias perception, making researchers see patterns in noise or miss mundane explanations. Some of these experiments were conducted by respected scientists who genuinely believed their results. They weren't committing fraud. They were making honest mistakes, misinterpreting data, or falling victim to subtle experimental artifacts. The cold fusion researchers thought they'd found unlimited energy. The opera team thought they'd found faster-than-light particles, but immediately asked for help finding the error. The arsenic life researchers believed they'd expanded the definition of life. They were wrong, but they were trying to do real science. Other cases are less charitable. The Hutchison Effect appears to be pseudoscience or fraud. The room temperature superconductivity claims by Rangadias show a pattern of unreplicable results and data concerns that suggest serious problems beyond honest error. What's striking is how long some of these failed experiments persisted. Cold fusion was announced in 1989, and people are still working on LENR. The Mpemba Effect was documented in 1969, and we still can't reliably reproduce or explain it. The Hutchison Effect was claimed in 1979, and believers still cite it today. Failed replication doesn't always end belief, especially when the claimed discovery is exciting enough. The replication crisis extends beyond these specific examples. In many fields, researchers are finding that significant percentages of published studies can't be replicated. Psychology, medicine, and other sciences are grappling with the realization that published results don't always reflect reality. The causes include pressure to publish novel results, statistical practices that inflate significance, publication bias against negative results, and insufficient emphasis on replication. Science is supposed to be self-correcting. Bad results should be identified and discarded through replication, but the process can take years or decades. In the meantime, resources get wasted chasing false leads, careers get damaged, and public trust in science can erode. The experiments discussed here remind us that science is hard. Reality is complex. Equipment can malfunction in subtle ways. Data can be misinterpreted, even smart. Careful researchers can be wrong. That's why replication is fundamental. And when experiments can't be replicated, when results appear once and then never again, we must conclude that something was wrong with the original experiment, no matter how much we wanted the results to be true.